Hey guys, this is Anand. Welcome to FluxEd. Today we'll be delving into the Prism derivation that you do in ray optics in class 12. Now the problem with this is it might seem easy at first, but at the end of the day everyone just mugs it up and yeah, whatever, they get the marks, but still, it's not about mugging stuff up. Physics is about not learning things by heart, but being able to reproduce it with logic. So that's what we'll be doing today. And this is somewhere where even like the toppers mug up. So that's not how the FluxEdians are going to be going about this. So come on, let's figure it out together. So let's create a prism first. I'm going with some general triangle. So let me say this angle is A, which is called the angle of prism. That's basically the angle that the prism makes. It's a property of every prism essentially. So that's A. Now let me say there's a light ray that's coming like this. So one thing that I did not write here is the outside medium is essentially air, and the inner one is that of, can be any material. Let me say it's mu. Anyway, air's refractive index is 1, and let me say mu is greater than 1. So mu is obviously denser, optically denser, which means if I draw a normal here at this interface, when light travels from rarer to denser, it's going to bend towards the normal. So it's going to be parallel to this base. Not mentioning that, but it should be understood. It's implied. Now if I draw the normal here, light is moving from a denser medium to a rarer medium, so it's going to bend away from the normal, like so. Now if I mark the angles, but before if I join these normal lines, I'm going to get something that I'll be using later on. So if I mark the angle of incidence as I and the angle of emergence as E, emergence as in like it's just incident on the prism, it undergoes some refraction and then it emerges out, so emergence. English guys. Alright, so first angle of refraction I'm just going to call it R1, the second one I'm going to call it R2. Now if I extend this first incident ray, if I trace back the final emergent ray, I'm going to get this difference. Now this is called delta, which essentially refers to a deviation. The total deviation makes, like after all the processes that are happening to the light ray. Now if I call this delta 1, delta 2, that essentially refers to the individual deviations. So over here, as you can see, light has bent in a clockwise manner, and here as well it has bent or refracted in a clockwise manner. So if we sort of mathematically visualize this, let's just visualize that for a second. We'll come back to the rest of it later. So from here we can see that I should be equal to delta 1 plus R1 and E should be equal to delta 2 plus R2. Straightforward stuff. Now delta, the total deviation, should be equal to the sum of the independent deviations. Now I'm putting the plus here because it's both clockwise. The bending is happening in the clockwise manner itself. Let me say if it was something like this, here light is bending in a clockwise manner. Let me say there's some medium here, mu. There's some other medium here, mu dash. So here it's going from rarer to denser, so it's bending towards the normal. Here it's going from rarer to denser comparatively. So rather than bending away from the normal, it's bending towards the normal again. So mu dash is actually greater than mu. So here, because of that, the bending will be anti-clockwise. So if I take the individual deviations as delta 1 and delta 2, I'll be getting the net deviation in this case as delta 1 minus delta 2. I'm considering clockwise to be positive and anti-clockwise to be negative. This is similar to what you guys did with torque and stuff in class 11. Just mentioning it. Alright, now that that's out of the way, let's get back to this. So from these two equations, we plug it in this, we'll get delta is equal to I minus R1 plus E minus R2. And finally we can conclude that this is how things are going to look. So I'm going to keep this to one side. We'll come back to this later. Next up, let me call this angle as theta. And I'm going to consider this quadrilateral, this blue quadrilateral. Now it's the intrinsic property of any quadrilateral that its opposite angles should add up 180 degrees. So A plus theta should be equal to 180 degrees. Now there's this triangle in here, this yellow one. We know that according to ASP, the angle sum property, all angles in a triangle must add up to 180 degrees. So from there we know that R1 plus R2 plus theta should be equal to 180 degrees. Now if I use both these pieces of information, I can conclude that so theta would be equal to 180 minus R1 plus R2, which will give you this. You can try this out for yourself, it's just basic math. So we have A is equal to R1 plus R2. Now this is a whole lot like this term. So that's exactly what we're going to be milking. So delta is equal to I plus E minus A. Therefore A is equal to, or rather A plus delta is equal to I plus E. This is one of the most important formulae in the Prism side of ray optics. So now that that's out of the way, let's check a very special case where delta is equal to something called minimum deviation or d minimum. In this case, what happens is angle of incidence will be equal to angle of emergence. Now why does this happen? Essentially, if there's some prism, there's some incident ray. So minimum deviation means what? Like the deviation should be minimal, like light shouldn't bend much, barely, to be honest. So that's like the aim, which means, let me say if it's hitting at some angle I, it should also reflect back at an angle I, which is basically your angle of emergence. So yeah, to minimize the deviation, this condition must be held true. So yeah, in this case, this would be d minimum. That's the logical side of things. You can prove this with a lot of complex math, but that's beyond the scope of our syllabus, so I'm not going into that. So let's solve for this. So I'm going to use this formula here. So d minimum is equal to I plus E minus A. Now I know that I and E are the same, so I'm just going to write 2I minus A is equal to d minimum. Now we'll be using this in just a minute. Alright. Now we know that A is equal to R1 plus R2. So in the case of d minimum, R1 plus R2 will be equal to 2R. Essentially these two will just equate out. So this will be R, this will be R as well. So from there you can conclude that A is nothing but 2R. So if you plug it in here, you'll get twice of I minus R. It's something that you need to know, but this is not the main result here. Alright, so from here we can understand that R will be equal to A by 2. Now this is something that's important. We are still talking about the case for d minimum, please bear that in mind. We are going to be continuing this. Let's take Snell's law now. So I'm considering the same interface for the prism. So as some refractive index mu, as an incident light ray that is hitting at an angle of, let me say, theta, or actually wait, theta, I itself, it's going where it has bent towards the normal. Let me say this is R. So I'm still taking the case of d minimum, please bear that in mind. So let's write Snell's law for this. So this is air, obviously. So that's 1 times sin I, which is equal to mu times of sin R. So from here we'll get mu is equal to sin I by sin of R. Alright, so from here we are going to be deriving I now. So I from here will be D minimum plus A. So basically I and E are the same, so I'll be like 2I, and then I'm going to take that to the other side, which will give us I is equal to A plus D minimum, or I'm just writing D for now. Yeah, A plus D by 2. Now we plug these two in, this guy and this guy, in the Snell's law equation. We'll be getting something that's really useful for us. So mu is equal to sine of A plus D by 2 by sine of A by 2. Now in ray optics, you guys in class 12 we deal with something called paraxial rays, which essentially means there's a light ray going, and this, let me say this gray line is your principal axis. These two will be parallel to each other, or like even if they make a slight angle with respect to each other, it's negligible. So whenever theta is small in mathematics, what we do is sine theta is essentially going to tend to theta, tan theta will also tend to theta, and cos theta will tend to 1. This can be easily visualized like tan of 0 is 0, sine of 0 is 0, cos of 0 is 1. So anything close to at 0 will be almost the same value. So you can visualize it like that. So obviously theta is in radians. Please bear that in mind. It's not in degrees. It's in radians. This is very important. So using the approximation that I just said, so A plus D by 2 divided by A by 2, we're going to be cutting 2, and we'll be left with 1 plus D by A. Now from here we can find a good expression for D. So from here D by A will be equal to mu minus 1. Therefore D minimum, please note that D refers to D minimum. I just said that, I didn't write that. That's my apologies for that. D minimum is equal to A times of mu minus 1. And this is a very useful result for us. So yeah, these are the most important equations you need in terms of the Prism topic. So yeah, bear these in mind. It's the minimum deviation formula. You must know how to write Snell's law for any given case, and we are just applying very specific case here for Snell's law. You must know how to manipulate stuff, and yeah, we are just exploring the case of D minimum the most. So you must know what the geometrical meaning of D minimum is. Then yeah, you must know the basic quadrilateral properties and how to manipulate them. Essentially what you've been doing in primary school. So yeah, as a pros at that, you must know to take the right symbol and the reason as to why we add the deviations up. This is something that I don't see a lot of people explaining, but yeah, this is quite important. You can use your talk analogy for this. Shout out to my physics sir for that, Kishore sir. So yeah, and yeah, you must know how to do this. Basically all the mathematical manipulations. So yeah, that's basically it from this topic. In case you have any doubts, HMU, I'll solve them for you, and I hope this really helped you and you found it insightful. So thank you and have a good evening or a great day. Ciao.